Today's lecture is about the dual of LP spaces, and at the same time we'll review some concept of Banach space. So you know this material is section 6.2 of Fallen, and there are some general facts about Banach spaces that are in section 5.1 and 5.2. Okay, so our favorite space, Banach space, is now LP for P between 1 and infinity included. So remember that Banach space is a vector space that is that has a norm, and under this norm it is complete. Okay, and all right. So now what we want to prove is that the dual of LP in most cases is given by LQ. So what does that even mean? All right, now let's go back to the definition of LP. So LP is the set of function on the measure space XMU, so that the LP norm, which is the integral of the pth power of f with absolute value, 1 over p to be sure that it's a norm, we want this to be finite. Okay, so we already proved that this is a vector space, it's complete. Okay, we've spent a whole class on that, and okay. Now, what is the dual? So the dual is the set of linear functional on that space. So it's a set of function that we call little l for linear from LP to R. Okay, such that L is linear and bounded. So L means L of f, L of f plus g equal to L of f plus L of g. What does bounded mean is that the if I look at L of f, then this should be smaller or equal than a certain constant, doesn't depend on f, times f of p. Okay? In other words, what is bounded is L of f divided by its norm. Now that induces actually the definition of norm for the dual. So what's the norm of the dual is just the soup of all the function LP of L of f and absolute value divided by f of p. And if you enter the f of p inside this, you can reduce it to the function f whose norm is small or equal to 1. Okay, so of course anytime you have a Banach space you can define this, and it turns out, and this is done in the notes, maybe I should say where, that any time that the target space, in our case it's R for linear functional, it's complete, then the dual is a Banach space. Okay. Now in the notes I consider L of xy, where you look at operators between Banach space S to Banach space Y, and operators are bounded and linear. Okay, so let's just focus on functionals where you really look at functions from our Banach space to R. Okay, good. Now it's easy to see just by linearity and boundedness that any linear functional is actually continuous, meaning that if I take a sequence of fm converging to f in LP, then if I take the distance, so just the absolute value between L of fn minus L of f, those are two numbers, right? It's a linear, it's a functional, so this is a real number and a real number. Then by linearity, this is just the absolute value of L of fn minus f. And this is smaller or equal by the definition of the norm to the norm of L times the norm of what's inside, which is fn minus f. Okay, therefore it converges if Fn converges to F in LP. This goes to 0, then this also has to go to 0. So any bounded linear functional is continuous. Good. Okay, so here's what we want to prove. We want to prove that the joule of LP is LQ. Okay. So what does that mean? So that means that to any element in the joule of LP, I can associate an element in LQ. And it turns out that this correspondence is also isometric, which means that if I look at the norm of the functional, okay, in the joule of LP, so the norm of this functional is actually the LQ norm of the element of this correspondence. Okay. Now a couple of warnings. So it's good to. This correspondence holds anytime when P is strictly between 1 and infinity. And if mu sigma finite, remember sigma finite is always appears often in our assumption. We need that for Radon-Nikodym. We need that also for Fubini's theorem, so that's not new. So if mu sigma finite, turns out that you need something a bit weaker than sigma finite, which is semi-finite, but let's just say sigma finite for now. And it's okay for P equals to 1. So in other words, the joule of L1 is L infinity, if mu sigma finite. Now the case P is equal to infinity, so what is the joule of L infinity? It turns out it's much bigger than L1. Okay? And so this is very different, so a little warning here. Now, it's easy to see that you always have the embedding, the following embedding. So to any function on LQ, I can associate a function in LP. How? I can associate a linear functional of LP. How? Just by integrating. Okay? So if you take a fixed function g in LQ, and I can define a linear functional. So LG here is from LP to R. Okay, so I take a function f in LP, and I integrate with respect to this fixed function q. So this is clearly linear because it's an integral. If I take a linear combination of f, I get a linear combination of integrals. And it's bounded. Why? Because of my good friend Hölder, which tells me that the absolute value of this integral here is smaller or equal than the LP norm of f and the LQ norm of q. And therefore, if I take the sup over f, right, that means that, and divide by this, it means that the norm of this linear functional I defined, it's actually smaller or equal than the LQ norm of G. Alright? So I have a bounded linear functional. Now, I told you that this was isometric, and in fact, the norm of LG is even better than smaller or equal to G. It's actually equals to G. And this you have to be a bit clever. If you read and follow and first you're like, oh, how do you think of that? Well, it's just you come up with a function f where you actually have an equality here. So you have to be a bit clever how you pick your function f. Okay? So you pick it like this. Okay? Turns out if you do the calculation, if I take the integral of the pth power of that, because of this relation, that 1 over p plus 1 over q is equal to 1, remember that p and q are conjugate, then pq minus p is equal to p, and actually what you get here is equal to q, and what you get for the LP norm of f is simply 1. Okay? So that's just a calculation that you can do right now. And therefore, once you know that, if I compute the integral of fg, and this is why I have this g over absolute value of g, that if you think about it, this is actually the sine, function sine of g of x, right? Then when you integrate over f of g, fg, what you get is, because of the q minus 1, you get the qth power, and everything cancels so that you get actually this, and so this is actually 1. So L of g of f with the special function f, which is a bit clever, gives you the norm of gq. Alright? So, at the end of the day, it is clear that I can define a linear functional by Euler by integrating simply on this function f. So this is the nature of this embedding. Now, if q is equal to infinity, so p is equal to 1, here you have to be a bit clever. You can look at the notes, and you can see that you need a bit more about your measure space. You need that you are semi-finite or sigma finite, and so I'll let you read that, okay? All right, so you have this embedding all the time, okay, even when q is equal to infinity. However, you only have equality when p is strictly between 1 and infinity, and p equal to 1 is also okay if mu is finite. So you want to go the other way, right? You always have this embedding of LQ in the joule of LP. So what you need to prove, and that's what we're going to do now, is to every functional of in the joule of LP, I can associate a function LQ. And the key for that is the Radon-Nikodym theorem. All right? So let's discuss the proof. All right. Go directly to the notes. So this is what I said. You always have this. Well, the embedding actually goes the other way. So you always have that. Okay. So we want to prove that you have this embedding is actually surjective and injective, and that you have this isometry. So the norm to every linear function of L in the joule of LP can associate a function LQ such that the norm, the operator norm of the functional, is equal to the LQ norm. Okay? All right. So how do you prove this? Well, you use the Radon-Nikodym theorem. So I should say also that we already saw this case in the case of L2. So already saw that L2 star is L2. It was the Riesz representation theorem that we prove using very specific tools of Hilbert spaces. Actually, this is true for any Hilbert space. And right, so that's what we did last time. So now we extend that a bit. Okay, so how do you prove this? We'll not do the full proof because you have to do several cases. But again, the key is Radon-Nikodym. Okay, so let's start when mu is finite. Okay, so what you're going to do is define a measure. So remember, Radon-Nikodym is about a measure that is absolutely continuous with respect to another measure. So we're going to define a sine measure, okay, from the linear functional. So how do you define that? So you define nu of E is simply the linear functional applied to the indicator functional characteristic function at E. Okay, so remember that I take this notation sometimes for characteristic function. Okay, so now how do I know that these functions are in LP? It's because that mu is finite. Okay, so note that Okay, so any set has finite measure. That's what I'm saying here. Okay? So we define this measure on this set. Now, it's clear that nu of the empty set is 0 because L of 0 is equal to 0 just by linearity. And also, how do I know that I'm finitely additive? By linearity of the functional. Okay. Now, to have a measure, so I want to know that measure is well defined, I need to prove sigma additivity. So sigma additivity is not hard. So how do you prove it? So you take a sequence of disjoint measurable set. Now you want to show that the sequence of indicator function converges to, in LP, to the indicator function of the union, the disjoint union. So again, this is not hard because the indicator function of a disjoint union is the sum of the set, and therefore I can write the difference like this. Okay, and this is just by definition, if you take the p power of that, because they're disjoint, I can rewrite it simply as this. Okay, so this, as n tends to infinity, goes to 0. Okay, because again by continuity of the measure, and that's it. Okay, so you have that the indicator converges in LP, and since we use the fact that the functional is continuous, therefore the measure of this guy should converge to the measure of this guy. Okay, so we're using heavily the continuity of the functional. Okay, now what we have to show now is where does this function g in LQ comes from, but that's Radon Nicodim. Okay, so I want to show that the measure I just constructed from my linear functional, that it's absolutely continuous with respect to mu. But again, that's clear because if mu of e is equal to 0, it's a null set for mu. I want to show that this is a null set for nu as well. But this is clear because nu of e is equal to, by definition, the function of the indicator function, which is small or equal to this, and the LP norm of the indicator function is the measure. Okay, if the measure is the p power of this is just this, and so the measure of that is 0. So this is equal to 0. Okay, so by the Radon-Nicodim derivative, so important point, there exists a unique g. Now so far I only know it till L1, so that nu of e is given by integrating of g of u. So at this point what I have is that L of the indicator function, so this functional, if I restrict it to indicator function, I can write it as an integral over this function g. This is what I have so far. Now I can extend that to simple function just by linearity of L, right? And linearity of the integral, so that extends to simple function. So two things are left to do. What do you have to do? You have to show that this works also if for any f in LP, not only simple functions, and also that g is not only in L1 but it's in LQ. Okay. So let's start with the second one, that g is in LQ. Okay. So the fact that so g is in LQ. So how do we show that? Well, again, it's a little bit a clever trick with defining the right function. Okay, so you look at the norm of your linear functional restricted to the simple function. We know that that's fine. Okay, and we showed that so we call this S, the supremum of the functional only on simple function, we showed that the supremum is exactly the LQ norm of G. Okay, that's the best we can do so far because our functional is only defined on simple function. Okay. All right. Now you have one inequality for free because the supremum just by Hölder's, right? So by Hölder's, this is smaller than the LP norm of F times the LP norm of Q, and LP norm of F is 1. So this is for free. Now to prove the reverse inequality, to show this, again, is to use this clever function Q. This clever function with the Q, okay? And so what you do is you take a simple function Gn, sequence of simple function Gn that converges to G. You can always do that. And the converges pointwise to G, I can always do that. We use that trick all the time. And you define this function Fn, which is also simple. And oh no, it might not be simple because of that G. Sorry, Gn is simple, but G might not be, so Fn might not be simple. Then by construction, this norm, LP norm, okay, with the same trick as I said before, is equal to 1. And therefore, the LQ norm of these Gn by construction, because of that trick, is equal to this, which is smaller than G, because we choose this Gn that converges to G from below, and everything is positive, so I can write that. And this is smaller than S because S is the supremum. Okay. Now you use Fatu, and you get that this Gn converges pointwise, so I can take this limit out. Okay, here this is the limit pointwise of the Gn, can take the limit out. And this is the trick that we use often. That is, if you have a function Gn, a sequence of function Gn that converges pointwise to G, then the LQ norm of G will be always smaller by Fatu. This is a typical trick. All right, to show that the LQ norm of the limit is small equal to the limit of the LQ norms. Okay, and so therefore you have what you want, that the norm LQ norm of G is smaller than this soup. Okay, remember this inequality. All right, so that shows that G is in LQ. Now, how do you extend this? That the fact that the functional, again, this functional, we only know that it's given by an integral over G for a simple function. How do you extend to all functions in LP? Use another trick, that is, simple functions are dense in LP. Okay, we know how to show this. We did that last week. So we take a sequence of simple functions that converge to LP. Now, because again the linear functional is bounded, is continuous, so L of F is the limit of L of Fn. I know that L of Fn I can write it as an integral. All right, and how do I know the integral of? So how do I know this limit? Now this is a bit using Hölder and linearity of the integral. I can write this as the integral of Fn minus F times G, and then by Hölder this is small equal to Fn minus F P G of Q. Okay, and therefore Fn converges to F, right? And therefore this guy converges to the integral of Fg d mu, which is finite. because G is in LQ and F is in LP. Alright, so that's the essence of the proof. Okay, I went maybe a bit fast, but again, what are the important points? I can define a measure using my linear functional. Okay, using the fact that it's continuous linear functional, I have the properties of the measure. How does the G arises? It's from the Lebesgue-Granoux-Nikodym derivative after realizing that the measure I define is absolutely continuous with respect to the reference measure. And lastly, I extend the representation of the functional as an integral to all functions in LP, simply using the fact that simple functions are dense in LP. Alright? Now you can extend to sigma finite by the usual trick, that is, you have the existence of this function Gn. If you restrict not to the analysis to a finite to a set of finite measures, say En, that converge, that goes to, that increases to x. Okay, so this is fairly standard. Now the extension to any mu, if p is between 1 and infinity, is a bit clever. I will let you read it, but I will not necessarily focus on it. Alright, so that explains again the idea for showing that the dual of LP is actually LQ whenever 1 is smaller than p smaller than infinity. Now if p is equal to 1, this is okay if mu is sigma finite, and in turn if p is equal to infinity, it's very special. We'll talk a little bit more about that. The dual of L infinity is quite large. Alright, thank you for listening.